Okay, so we'll continue. So far, we have seen reduction from vertex cover to 3 different problems, basically using local replacement. As far as homework and exam is concerned, that's basically about 50, almost enough, except something we are going to discuss later in this class, in this lecture, okay, after 20 minutes. So we'll discuss restrictions, something simpler. Other than that, that will be good enough, I think, okay? So basically, you use ideal local replacement will be good enough for you. Next example we are going to discuss is actually more subtle. Oh, it's okay. Yeah, I think students know how to do these things. Don't worry at all. Okay. These students are very experienced already, 30 years, so they know all these things. Don't worry at all. It will work. Okay. No need to worry about this. Sylvia. Okay. No need to worry about these things at all. Okay. We can just leave them to do it offline. So students know how to do these things. All right. Okay, so let's see. So what we have now, the dominant set is also an NP-complete. Now we are going to discuss a reduction from vertex cover to subset sum. So this one is not obvious at all. If you look at these two problems, they're totally irrelevant because subset sum problem is we have a collection of numbers, the integers. I just remind you what the problem is. And we need to find a subset whose sum equal exactly a given number, say 100. Is it possible? So these two problems really look totally irrelevant. And how come we can reduce vertex cover to subset sum? It seems almost impossible. So that's the amazing part about polynomial reduction. Very often we can have relation between two totally irrelevant problems. So I will give you a taste here to see how we can reduce vertex cover to a totally different problem, subset sum. All right. So that's one we are going to discuss first. Afterward, we are going to reduce some easy ways to prove NP-completeness, which occur very often in practice. And will also apply to maybe homework and final exam. Maybe, okay, I'm not sure. I cannot give you too much about final exam questions. Otherwise, I've done it for you, okay? All right, so now we're going to give a reduction from vertex cover to subset sum. Now, the most difficult thing is they seem to be totally irrelevant. So vertex cover is a graph and the integer k. In subset sum, we have a collection of integers, set of integers, say positive integers. So from positive integers, all right? And we have a target value. It's also a positive integer. So it's totally, we're really dealing with totally different things. And we want to know whether exists a subset whose sum equal to W. So how is it possible? Vertex cover dealing with graphs, and now we're dealing with summation of numbers. So intuitively, it's almost impossible, right? Does anyone have an idea how we can do this? Anyone think it's possible? If we just ask you to randomly guess, wait, the graph is unweighted. Sorry, yeah, but the problem is the graph is unweighted. Even if it's weighted, actually, it's not. Okay, this graph is unweighted. So first, how can we come up with these numbers? If I just ask you to guess, say it's a final exam problem, ask you whether it's possible, just you use the educated guess. And my guess, if I did not know these things, I would guess no, almost impossible, with certainty almost, right? It's almost dynamic programming. How is this possible? Good idea, but yeah, a wild idea. Okay. Now we only need to construct a single instance. We are not going to find a solution. Yeah, degree is good. It's something. Okay, so you see, it's not easy at all. Okay, the first thing is really how can we construct these numbers? How to construct these numbers? So you have to construct integers from a graph at all, right? From graph G. So that's a big question. Yeah, you are getting it. Matrix. Yeah, you are getting there. Good, good. So matrix. Now, a graph can be represented by a matrix. All right. So if I have a graph, say V1, V2, very good guess. That's very, very good. I have a matrix. So I have V1, V2, V3, V4. V1, V2, V3, V4. So it's 0, 0, 0, 0, 1, 1, 0, and so on. I have a matrix. All right. Now, once we have matrix, of course, it's closer to a number. It's not integer yet, but it's closer. However, one big problem with this matrix is the information about relation between edges and vertices are kind of implicit, are hidden in this matrix. Because vertex cover really dealing with relation between vertices and edges. However, this matrix dealing with relation between vertices. So information of edges are there. For example, this is edge. Right? So this one is edge, 1, 2, 2. But it's kind of hidden. It's not explicit. It's not easy to extract that information from this matrix. But it's a great leap. Once you get the idea of matrix, it's really a great leap. All right. Now, other than this matrix to represent a graph, there is another important matrix. Usually we don't use it. Recall how we can represent a graph in terms of data structure? Adjacency matrix. Another one is adjacency list. What is an adjacent list? How can we represent a matrix from an adjacent list by a matrix? So actually, we have another matrix called incidence matrix. Incidence matrix of a graph that will represent relation between vertices and edges. For example, for this one, against this graph, so we can use adjacent matrix to represent this graph. Also, we can use so-called incidence matrix. So each edge we also give it a name, say E1, maybe E2, E3, E4. All right. Now, instead of using adjacent matrix, we can use incidence matrix, where those may be vertices. So we have V1, V2, V3, V4. Now, columns are edges. For technical reason, for notational convenience, I will list edges in reverse order. Instead of E1, E2, E3, E4, I will list them in reverse order, E4, E3, E2, E1. That will be for technical convenience. Later on, you will see the reason. All right. Now, if edge vertex is incident with an edge, we put 1 there. Otherwise, it will be 0. So it will be 1, 1, 2, 3. So these two are 0. So vertex 1 is incident with these two edges. These two edges. It covers these two edges. Okay, in terms of vertex cover, it covers these two edges. Now V2 cover E1, E2, E3. That's V2, right? And V3, E1 only. V4, 3, and 4. All right. So that's called incidence matrix. So we have relation between vertices and edges. So now we have a matrix. How can we use matrix to produce numbers? For ordinary people, maybe it's not easy, but for computer science students, it should be quite obvious once you see a binary matrix. For any guess, how do we obtain numbers now once we have a matrix? For us, it should be trivial because it's second nature to us, or second nature of us. A squared, okay, too complicated, much simpler way. For us, each row is a binary number. For computer science student, it's a binary number, right? That's 9. That's 7. That's 2. That's oh, sorry, did I made a mistake? That's 12. That's 12, right? Now we see how can we can get numbers. All right. So we get these numbers. Now do you see connection between vertex cover and these numbers for subset sum? Now vertex cover, say, let's see, for this particular graph, vertex cover maybe 2. Say, if we use the 2, 4, say. Okay. Now it's difficult to see if a number is represented by decimal, but if a number is represented by binary, the connection is easier to see. All right. So V2 cover, if you look at the second row, so that means edges with 1 there. So 2, 1, 2, 3. These are covered by V2. Right? In the V4, edges with 1 there, E3, E4 are covered by V4. Now, if you look at a row, at a column, maybe use different. What can we say about every column? Something. How come this one? Maybe I made a mistake or something. Why I happen to have everyone covered exactly twice? Oh no! Sorry, no. It's not. Okay. Maybe I should highlight this one. No, that's too messy. Maybe mark a star here. No, it's okay. Just staying this way. If we look at each column, no, not exactly 2 ones. Each column contained at least 1 1. Maybe I should say selected one, or chosen one, selected one. So here we select V2 and V4. So among these two, it contains at least one of them, one of these chosen vertices, or at least one selected vertices. Yes. instead of one, say selected vertices. By definition of vertex cover, corresponding to selected ones. Some may contain 2. So this one is exactly 2. So let me highlight it. So this one is exactly 2. This one is 1. All right. Now, actually, this suggests our target, if we set our target to be target sum, W to be 2, 2, 2, 2. So there will be M of them. Now so that will correspond to vertex cover. Vertex cover actually will give us maybe 2, 1, 1, 2, 1, 2, or something. So some is 1, some is 2, not all 2s. But we'll fill some of the sum, right? For vertex cover. It covers all edges. If edge is covered twice, it becomes 2. If only covered once from one end, it gives us 1. So we'll be able to fill at least the sum half. Sum of it partly will fill up this sum. But that's not good enough. Because exact sum, we want it to be all 2s. So there's a distance between what we can do and what we have been done, and what we need to do. What we need to do is all 2s. But now vertex cover will enable us to do this part. It's still some distance away. So what can we do? So we'll create some new numbers. Other than these numbers, we also create some new numbers. So new number will have use a different color maybe. Okay, so 1, 0, 0. Let me see. So it has 1 in each position, exactly 1, 1 in each position. Oh, sorry, this is 0. 0, 0, 0. Sorry, this should be 1. 1, 0, and 0, 0, 0, 1. So create some new numbers. All right. So these numbers they call y. So these number may be called x. So from x1 to xn. So these numbers use. So x1, x2 up to xn. So here I create some new numbers y. So here's I use. So here should I also mark it in this order? This ym minus 1 up to y1. All right. Now I can add up. So I can, in order to make 1 to be 2, I can choose a number from y to make it 2. So here, E2 is, this one is missing. So what I can do is choose this one. Also add this number. E1, this one is missing. The first digit missing, I choose this one. E4, this one is missing, I choose this one. Okay, so these numbers are 1, 2, 4, 8. All right. Now, in order to make all 2, other than these numbers, 7 and 12, let's see, 7 and 12, I also add these 3 numbers. So these numbers together will allow us to get 2, 2, 2, 2. All right. Get the idea? Okay. Okay, it's normal if you haven't get the idea. It's really subtle. It's not easy at all. Totally lost. Okay. So let me maybe try to explain again. Okay. Yeah, I think it's very normal. You get totally lost. It's not easy at all. It's really a subtle reduction. But once you understand it, it's a very beautiful reduction. So what happens? So this part, is it okay? We create these numbers. So each one corresponding to a row. Each row define a number. All right, but these numbers, the solution part, do not add up to all 2s. So in order to make them to be all 2s, we create a number So that will enable us to pack them completely. So you can think about this one as a packing problem. So we have m dimension. Each dimension is exactly, we need two. Each dimension gets to exactly 2. But by choosing some number from here, it will be not enough to get 2 exactly for each dimension. So in order to do that, for each dimension, we create a number. So that we choose some number from these particular number y, then we can get exactly 2 for each dimension. So for each dimension, we need exactly 2. But by choosing some number corresponding to vertex cover only allow us to choose 2 in some dimension, but some part maybe only 1. So in order to reach 2, we choose some number from here. Once we add them, then we can also get to 2. All right. Okay. I don't think it's realistic that I can make you fully understand this one, but to get some basic idea will be good enough. Anyways, I know it's maybe too complicated for most of you. Basic is the idea. Actual construction is not really complicated. Okay. Now, let me finish the explanation first. Now, how does this GK, this K corresponding to subset sum? Actually, we use this K to control the weight. We choose K vertices. So each vertex, if we choose them, we get actually add 1 here. So each number actually is not exactly 9, 7, 2, 12. We need 1 number here, because otherwise we cannot control it, how many vertices we choose. All right. So then the number here becomes K. So actual number we use, well, in decimal is K. The weight is K2. That's the number we need to add up to. All right. Now, actual number we produce for this part is not exactly these numbers, but rather we have a 1 here. So we have a 1 here. So it will be 10 to m power plus this number. In decimal, it's this number. I guess you get even more lost. All right. Anyway, I think I better stop, okay, without getting to all the details. Otherwise, I just get you really totally lost. You really need, if you really want to understand how it works, you need to spend maybe 15 minutes or 30 minutes at least after class and try to dig into details. Oh, actually, that's a simple example. Yeah, this one give you a simple example. Let me try to yeah. I give you this one as a simple example. Make erase something first. Okay, erase something first. Otherwise, too messy. Okay, erase these things first. A vertical one. I think I want also erase this one. Okay, so the actual number we construct for these 4 columns, here will be 1, 10009. Here's 10007. Here's 10002 and then 10012. These are actual 4 numbers we construct. And plus these 4 numbers, 8421. So these will be our numbers corresponding to this graph. These will be our actual numbers. And if k equal 2 here, in this case, k equal 2, then our number is 2, 2, 2, 2, 2. That's our W. All right. So I think I better stop discussing of this particular reduction and give you this example. If you really want to fully understand it, you can look at this example to see, and also look at the notes. And actual notes is only some formulas that not really explain the reason behind it. Okay. Yeah, good question about this K. Actually, K means this is 10, sorry, it's actually this number means K times 10 to m's power. All right. So that's why I add verses from EM towards E1. All right. But anyway, I think I better stop here. Anyway, yeah, otherwise we will not have time to discuss another important technique. All right. So that's why I just want to give you a taste. I do not really hope you can fully understand this one just with my explanation. It's because it's really subtle and the things are kind of maybe are kind of awkward to you. It's from vertex cover to subset sum. It's something totally new. All right. Okay. So let me just summarize the basic idea in this reduction. So we use incidence matrix. If I can explain these things face to face, maybe it's better. It will be easier. But unfortunately, it's Zoom. Okay, incidence matrix. So then each row will give us a number. So each row will produce a number. That's an integer. All right. So that's the basic in the reduction. So these 4 rows will give us 4 numbers. And then in order to make it all true for this part, we create these numbers. And we can only use this number only once because of the way we construct these numbers. It's the power of 2. All right. So that's a basic idea. I think I better stop here. Maybe too demanding. All right. I think if you really want to understand it, and you need to spend at least 15 or 30 minutes after class. But I think my explanation should help you to understand this one. All right. Of course, this one will not be in the homework, not in the final exam. This reduction is too much. All right. Now, actually, once you understand it, it's not difficult at all. Once you understand it, but your brain is not really get used to this type of reductions. It does not. Your brain is just it's look quite awkward to your brain, so it takes time to become your idea. All right. So anyway, I think I better stop about this problem and talk about something else. Otherwise, you're stuck with it. Okay, forget about this one for the time being. Okay, if you're really interested, you can study it afterwards. If you still don't understand it, you can discuss with me, and I will try my best to explain to you. All right. Okay. All right. Okay. So what we have so far is now our toolbox is much larger. We have these problems. I add 2 more problems. Certainly, I will not discuss reductions. Otherwise, you will get. Okay, anyway, Hamiltonian path and Hamiltonian cycle. These 2 problems, Hamiltonian path and Hamiltonian cycle. So these 2 problems are also NP-complete. So these are problems of finding a cycle that visits each vertex exactly once, or cycle visits each vertex edge, a path that visits each vertex exactly once. So the cycle path visiting each vertex exactly once. So that's a Hamiltonian cycle, a Hamiltonian path problem. So for example, of course, for cycle, you can say one vertex is a starting point and ending point. You can say twice, but actually regarded as once. For example, I give you an example, then you see what I meant. A starting point and end point depends on how you regard it once or twice. All right. So this one has a Hamiltonian cycle. You can start at this vertex, visit each vertex exactly once, and come back to the starting vertex. So that's a Hamiltonian cycle. Or if you don't like this definition, you can say a spanning cycle. A spanning cycle. So it's a spanning cycle. So it's a cycle containing every vertex. That's called a spanning cycle. All right. So this one has a Hamiltonian cycle. I'll give you an example where it does not have a Hamiltonian cycle, but it has a Hamiltonian path. As a famous Peterson graph. Okay, this graph does not have a Hamiltonian cycle, but it does have a Hamiltonian path. I think I can randomly draw one. I think I have a very good chance to find the Hamiltonian path. Yeah, I do. So starting and ending velocity will be different. So compare with the Aurelian path, Aurelian cycle. So it's a vertex counterpart of Aurelian path, Aurelian cycle. So Aurelian cycle visit each edge exactly once. Here we visit each vertex exactly once. So while Aurelian cycle is easy, it can be done in polynomial time. Here, the problem of Hamiltonian cycle and Hamiltonian path are NP-complete. Okay. So these are important NP-complete problems you should remember. 3 set, set and 3 set, same thing. So basically, 3 set, just the same problem, vertex cover, dominating set, subset sum, of course, and there are partition. So basically same problem, okay. The tutor gave you a reduction between subset sum and partition already. So that's your partition is also NP-complete. We want to partition a set of number into 2 parts with equal sum. That's called partition. And also Hamiltonian paths and Hamiltonian cycles. All right. So these are the basic NP-complete problems. And normally when we try to prove that a problem is NP-complete, we will use one of the problem inside. Usually these problems will be good enough. Otherwise, if there are too many problems we can choose from, it will be almost impossible. Now we can only restrict our attention to about 5 or 6 different problems. So whatever problem you want to prove to be NP-complete, we can choose one from these basic problems. That will make our task possible. Otherwise, it will be impossible. All right. Okay, so once we have these things, that will give us another important way to prove a problem to be NP-complete. That is called restriction or generalization. This book says generalization, but usually we say restriction. So in order to prove pi, you probably maybe say pi is empty hard. What we need to do is a special case what we can do is, if we know that a special case of pi prime is NP-complete, then of course that means pi is NP-complete, because pi is more general than a hard problem. So if that's domain of pi, and here's domain of pi prime, so we know this part is hard already. Of course, to solve this problem, pi is difficult, because if we can solve this pi, the whole thing can be solved. Of course, we can solve pi prime. So that's the idea of restriction or generalization. So in order to show that the problem is difficult, we show that a special case of the problem is difficult. So basically what we do is just find a special case of the problem from our toolbox. So we show. So in practice, what we do is or anti-hard or anti-complete and not matter really. Okay, so because we're only about hardness. So what we need to do is show that some NP-complete problem or NP-hard problem is special case of our problem. That's good enough. And typically what we do is by given particular values, give a particular value to the argument in the problem definition. Say parameters or arguments. Say parameter, okay, for the time being. Involved in problems. All right, so by giving particular value to parameter involved in problems, we get an NP-complete problem or NP-hard problem. So that's how it works. So let me give examples and you will see how it works. In practice, very simple. Okay, so I'll give you quite a few examples. Maybe you should say long path instead of longest path. All right, so here's the long path problem. I give you a graph, ask you whether the graph contains a path of length at least k. All right, this problem is NP-hard because Hamiltonian path is a special case of this one. It's a special case. Because if we specify this k to be n minus 1, we get exactly Hamiltonian path. The longest path in a graph contains at most n minus 1 edges. So by setting k to be n minus 1, we get exactly Hamiltonian path. So because Hamiltonian path is NP-hard, so this one is NP-hard. All right, so if we change path to cycle, if we're looking for a cycle of length at least k, then Hamiltonian cycle is a special case if we set k to be n. So Hamiltonian cycle is a special case of long cycle. Okay. Now if we stay on cycle, but the graph maybe instead of unweighted graph, now this one is weighted graph. So if we say weighted, so here the heaviest cycle maybe, or maximum weight cycle maybe. So is there cycle of weight of total weight. All right, so instead of a graph, now if we consider weighted graph, so whether this weighted graph contains a cycle whose total weight is at least k. Now this problem is NP-hard. Is NP-hard because Hamiltonian cycle is a special case. So special case is weight, each edge gets weight 1. So when each edge, weight of each edge is exactly 1, and k to be n. So we get Hamiltonian cycle. So this one gives us Hamiltonian cycle. The problem becomes Hamiltonian cycle. So Hamiltonian cycle is special case of this one. Therefore, this weighted version is NP-hard. Okay, now one thing to be careful here, it only shows the problem is NP-hard. Because special case is NP-hard shows this problem is NP-hard. But because it's more general, the problem itself may not be in NP at all. It's possible, but usually it's trivial, it's in NP. So be careful here. It only shows that this one is NP-hard. Maybe it's in the previous, in one page. Yeah, so here. Okay, so here it shows it's NP-hard, not NP-complete. Not the NP-complete. In order to say it's NP-complete, we need to add it's also in NP. But this is not implied by the property of its special cases. That's something different. All right, but normally we concentrate on the hardness. All right, so this one is really very simple. I give you a few more examples. I give you 2 more examples. In 2 or 3 minutes, it's possible. Because this one part is really very simple. But it takes a while to get familiar with this one. Degree constrained spanning tree. All right, so in a graph, we can find the spanning tree by DFS or BFS. All right, but the degree of the spanning tree may be different. For example, if I use this one, the maximum degree here is 4. So here we want to bound the maximum degree by a given number. We don't want to have larger degree, but in terms of communication network, if we use spanning tree as backbone, the load of site, so it cannot be too large. If a node degree is too large, so the load of that site will be too heavy. So that's why we want to bound that maximum degree. All right, so question asks us to construct a spanning tree, but with a degree bound. Anyone see like a particular problem in a special case? Actually, we don't have many choices. It's certainly a graph problem. So certainly cannot be a clique or independent set of vertex cover dominant set. Only possibility is something dealing with ordinings. Cycle, path. So actually, if we set D to be 2, then we get Hamiltonian path. Once the maximum degree is 2, the spanning tree looks exactly like this, which is a path. So Hamiltonian path is special case. All right. Let's see. I think I better stop now. Maybe give you a few more examples on Thursday. Okay. Yeah, I think I should stop now. Just talk a little bit about final exam. Maybe you're more interested in final exam. All right. Uh, in terms of format, I will give you, we'll upload maybe two past exam paper. Actually, you can get them from library. But anyway, I upload two past exam papers today, okay? One is 2 years ago because the year before I did not teach that one because the department required me to teach discrete math. They could not find anyone to teach discrete math. So there was 1 year I did not teach it. So the exam paper is 2 years ago. It's 208, 18, I think. But that one is multi-choice questions. So this term, it will be different. I cannot use multi-choice question because open book and because we have also online exam and face-to-face exam. So multiple choice is not good. So it will not be of that form. This year, basically, it's basically just what kind of, it's not multiple choice questions. There are a few yes/no questions, but be careful with these yes/no questions. There are 6 of them. Okay, if you don't know the answer, don't answer it because if you give a long answer, 1 mark will be deducted. So instead of getting 1 for correct answer, you do not get 0 mark for incorrect answer. You get a -1 for incorrect answer. So do not guess unless you are absolutely sure. Otherwise, do not answer it. Okay, there are 6 of them. Then others, about half of them are just ask you to find a solution for a particular instance. So that means you need to get familiar with these algorithms. So these simple ones. As I mentioned earlier, I give you 6 or 7 different problems for you to remember. For example, reduction, 3 set to vertex cover, you must remember it. Dynamic programming subsystem, divide, conquer, merge, sort, multiplication, a greedy algorithm, minimum spanning tree. I really strongly suggest you do a review on these things, really get to understand these problems very well and do a review and maybe summarize into a few pages, 2 or 3 pages at most for these problems, plus something else. Open book will not help you a lot if you actually does not help you at all if you take a textbook or notes for your exam. I don't think they will help you at all. Okay, will not help you at all because only 2 hours. Of course, when I designed the exam questions, I have taken everything that I can think of into account. Try to not make the problem too difficult for you. The level of these problems are similar as closed book exams. So what I did is I tried to avoid problems that you can obtain answer easily from notes and books. So try to avoid these problems. So basically, answer to these problems you cannot obtain it easily from notes. You have to work out something by yourself. Of course, it's almost impossible to ask you to design a brand new algorithm within 2 hours. It's almost impossible task. There are a couple of problems that ask you to design algorithms, but these are very basic ones, simple ones. You can modify some existing algorithms, then come up with the algorithm for the problem. All right. Except there may be one problem that may be not that easy, but the marks for that problem is only it's very small, maybe 3 marks. So those are really for students who really want to get 80%, 90% to get A mark, grade A or A minus. Otherwise, you don't need to try these ones. Actually, the answer to these problems not difficult, but it may not easy to come up with the idea. The final solution actually is very easy. All the solution for the problem in the final exam are very easy. But to come up with these solutions may not be difficult, maybe difficult. As I said, it's really hard to obtain marks below 50. So if a full exam is 100%, to get below 50 is really hard. It's really hard to imagine if you have studied this course, you can get below 50. I will be really amazed if you can get below 50. Even amazed, then someone gets 90%. Of course, it's not easy to get above 90% because I cannot give A grade to everyone, right? So some have to get some grade lower than A, or A minus, or B, or something. So that's why I have a couple of hard problems, but the percentage of marks for these problems very, very low, about 10%. Other than that, I do expect most of it get 70 marks at least. So my average, I think I aim for about 65 average, between the 65 and the 70. But the problem is this year, we don't have, no, I cannot ask the TA to try it because for security reason, who knows if something happened, then I will get into big trouble. So I cannot release this exam paper to anyone, okay, before the exam. All right. So, but this term, because we don't have middle term exams, so my feeling may be not as good as before. Usually, my average will be very close to a real situation. Certainly below, like within 5%, usually. Sometimes maybe 1 or 2%, even closer. But this time, I'm less confident because of I don't have we don't have a midterm exam, but I think it should be very close. Okay, so that's what I can tell you. So I really strongly suggest you prepare a couple of pages of notes by yourself, summarizing some important things instead of taking full set of notes and textbook to the exam. That will not help you. All right. Yes, that's how it works for online exam. You should handwriting your solution. I will post this thing on the homepage, to the homepage. Okay. And you should handwriting. For online one, because of the, everyone knows it's possible that someone may want to take advantage of online exams. So I have to be careful for online exams. Okay. All right. Any other questions? Okay. So on Thursday we'll get. Oh, by the way, no tutorial on this Thursday. Then next week, after you submitted homework 4, I ask TA to post the solutions. Okay. So no tutorial this week. All right. Okay. I think that's it. It's time for lunch. Yes, certainly I will look into it when I mark final exam online and face-to-face to see if a huge difference. If there are huge difference, maybe something's wrong. Okay. Not because of the problem itself, maybe the behavior of student. All right. Yeah, you can bring anything. Okay. But only the paper materials. You are not allowed to bring computers to exam site or whether online or face-to-face. Yeah, whatever notes you want. But actually, to be honest, that would not help you too much. It's better that you prepare a few pages notes by yourself after you reviewing course materials. Yeah, as I said, I will post the uploaded paper today. Okay. It's not new type of questions, similar to some old exams. I will post them in the afternoon. All right. Okay. All right. Any other questions? All right, so see you on Thursday. I will continue restriction method, and then we'll talk about approximation algorithm. Very briefly introduce a brief approximation algorithm. Then next week, actually lecture will be over this week. Next week, I maybe spend an hour to discuss FPT algorithms. Okay, if you are interested, you can attend that. If you're not, don't waste your time. Okay, these will not be in final exams. As I said before, final exam will only cover up to NP completeness. Yes, sure, I will record them. Okay, all right. Okay, time for lunch. Bye bye. See you on Thursday.